Okay, welcome to second lecture in the harmonic waves series. We want to address the issue of energy when wave is moving in a simple system of a wave generated on a string. This is although we're going to use just this language, but it's the same for other waves also. So waves traveling. So this is a transverse wave on a taut string. A string has tension T and it's got a mass density mu, which is mass over length. So we want to know, if I look at a small part of the string which used to be here, so the equilibrium is this line, which is along the x-axis, and displacement from this is the psi, right? So psi of xt is the dynamical variable. Okay, we want to know what is this energy of this mass that sits there. So mass there will be dm, will be mu times dx. So I want to know what's this kinetic energy, what's this potential energy. Add them up, I can get the total energy of this mass, right? So how do I get kinetic energy? Let's look at kinetic energy, and then we're going to look at potential energy. Well, I need to know it's over here right now, right? And it's moving. So I have half mv square we want to implement, but in these variables, right? So mass is this mass, okay? How do I get the v? Well, psi tells me psi at this point tells me the displacement, right? So we are going to get v is going to be d psi dt at this point. So if this was the coordinate, say x, so this will be at x t, like that. Or you can say y dot, but we're going to use the psi for us to denote y. Kind of crazy, but because of consistency in the same letter to represent the waves, we are doing this, okay? So we are going to get kinetic energy. So we are getting kinetic energy not for the whole wave. So we're getting kinetic energy of a string between x and x plus dx. So that's what we're going to get, and that is equal to half mu d psi dt square dx. So this is basically, I'm getting a kinetic energy of a very tiny element. That's why we're getting dx here. Makes sense, right? So if you can see, if I divide whatever I got here by dx, I'll get a kinetic energy density, kinetic energy per unit length. You can see that concept coming up, energy density concept coming up, just because it's coming over here. Okay, so that's kinetic energy in that, and let's figure out the potential energy in that part of the string. Potential energy. So potential energy, well, I have a tension here, T, and so this potential energy is stored, right? So some string has tension T, and I pull a little bit further out, means how much work I have to do? Well, that will be against tension and how much I pulled, right? How much the length changed. So it should be equal to tension the times new length minus the old length. So that should be the work I did, and that must be stored here, right? So that will be, and it's all differential, so it will be like a du, like this will be de, so a dke, and we'll just use a dk instead of ke. Capital K we'll use for kinetic energy, and small capital U you're going to use potential energy, and D just saying is I'm looking differentials. The task is to figure this one out in some reasonable way. Okay, so what's ds? Ds will be at whatever the size it is, but we can approximate to be linear there because infinitesimal. And if you this side is same as d psi, and this side is dx, so this is t. ds will be square root of dx square plus d psi square minus dx. And so if I pull the dx out, so you have a dx 1 plus d psi over dx. Because psi is a function of two variables, I go to the partial. So if I looking at this being very small compared to 1, so we can make a approximation. Expanding half gives me 1 plus half. You can do Maclaurin series. Suppose if you have 1 plus epsilon to the power half, what will you get? Epsilon is small, you're going to get 1 plus half epsilon. If you don't believe me, you should do the Maclaurin series and see if that's the case. All right. So half d psi over dx is square minus dx. So this is not exactly equal, but when this is very much small compared to 1, I can do this. And you can see the dx cancels out, and so this gives me half t d psi dx square dx. So this is the du, this is dk. So I get total energy in the energy will be sum of these two, right? Energy is a kinetic energy plus potential energy. So energy in element dx, right? I'm looking at that. So dE will be dk plus du, and you can see it's got something times dx. So if I look at inside, something to do with mass and something to do with the velocity, and then this one is actually looks like a potential energy. You can see half mv square, almost like that, right? T d psi dx square. So this looks like half mv square plus half kx square. Kind of looks like that, but they're analogous to it, not exactly the same thing, times dx. So this is the energy in there. How much energy is in the whole string? If the string is very long, I have to sum this up for every one of them. So I need to integrate it to get the total energy, right? And turns out if this string is infinitely long, there's going to be infinite energy. But if this is finite, it's going to be finite energy. So for harmonic waves, we can do integrate this over one wavelength. So energy so from here to here, so one wavelength, so this much string, the energy in that. Hello, in an earlier recording of this video, I kind of skimmed over this, and I want to go complete that. I think this is instructive to go over it in detail. All right. So this was energy in an element from x to x plus dx. And the wave, we're looking at a harmonic wave, and we've set phase constant to 0. So if I look at d psi dt of this, I'll get cosine going to sine, and then minus will come out here. So it's going to be omega a sine kx minus omega t. And d psi dx, this will be needed for potential energy, is going to be cosine will turn to sine, bring a minus, and then k will come out. So k times a sine kx minus omega t. Okay, so when you look at dk is going to be 1/2 mu d psi dt square dx, right? So this will be half mu, and we'll have omega square a square, and then we are going to have sine square kx minus omega t, and then we have dx. And du will be half t d psi dx square dx, and that's going to be half t k square a square sine square kx minus omega t dx. So when I put them together, so the dE is just the sum of these two. So half a square mu square omega square plus t k square sine square kx minus omega t dx. When we you can say that t over mu is actually, if I pull mu out, say I pull mu out, mu square, so this is not mu, there's no mu square here, there's mu, till mu out, so these actually equal to each other. This is omega over k, omega over k square, right? So this make a square, and because of that you will cancel the mu, t over mu times k square is omega square. So this actually is half mu omega square a square, and omega square plus makes it full sine square kx minus omega t dx. So we find this to be a really nice and simple of total energy, mu times omega square a square sine square kx minus omega t dx. And I want to go over the calculation for how much energy is in one wavelength. So let's raise this. How much energy is in one wavelength? So I have, of course, this wave is forever, goes forever. So just pick from here to here, and you have one wavelength, and this is the x. So I can go from x equal to 0 to x equals to lambda. And I can try to integrate this. What do I get? Well, you can do more complicated integration. You can just expand this, and then you can say sine of kx minus omega t. I can expand this as sine kx cosine omega t plus cosine kx sine omega t minus here, okay? And then I square this, and then generate terms and then integrate. You can see that in the x variable, when you integrate over 1 lambda, you're actually integrating over, as far as sine is concerned, 1 period, and sine is going to concern 2 periods. So when I integrate, I am going to get half lambda, and because this will give me lambda. You could convert this into half times 2 sine square theta for all that stuff, and then you can get half 1 minus cosine 2 theta, and you can see when you integrate that guy out, you're going to get 0. When you integrate that guy out, you're going to get lambda. So if I integrate dE over 1 wavelength 0 to lambda of mu omega square a square sine square kx minus omega t dx, I am going to get half out of it, half lambda out of it, half lambda mu omega square a square. So that's the answer I'm going to get. Let's stop it here. Just want to go over carefully.